Now, the last thing I wanted to end on in this week's series of lectures is give you a flavor and idea of really why we spend so much time talking about significant digits, why we really care about precision at the end of the day. An important place that we need to know as engineers the significant digits or the precision of a measurement is calculating the concentration of a very toxic substance that maybe have been released into the environment. Earlier last year, there was a large train derailment disaster in East Palestine, Ohio, in which a train carrying a large amount of industrial chemicals derailed and spilled many of those chemicals, and in the response, a lot of toxic substances were released into the surrounding soil, water, and air. Obviously, these are heavily populated areas with a lot of people who were evacuated very, very quickly. But because those people live and work there, the natural question is how do we know that the concentration of these toxic, very, very toxic substances have fallen down below a permissible level or fallen down all the way to zero? How do we know the precision of the measurement of a very small number to be confident that it is zero versus being a very, very low but still deadly or lethal concentration? For that, we really need to care how precise our measurement and how precise our calculated values are. Let's say that we're worried about one of the particular chemicals that was produced in this accident called phosgene. Phosgene is actually a World War I chemical weapon that was produced accidentally as a byproduct of this disaster. But it was a gas that was released into the air and into the water. Very, very deadly. A very small amount of this chemical can cause a lot of adverse health effects. The EPA, the Environmental Protection Agency, sets a permissible threshold of phosgene at 2 ppm, which stands for parts per million. It's a concentration unit, essentially meaning 2 grams of phosgene per million grams of air, or often for gases, it's 2 liters of phosgene per 2 liters of phosgene per million liters of air. By stating it as 2 ppm with effectively one significant digit, the EPA is communicating that they're not super confident on the exact value of this threshold. They know it's in this range, they know it's in this order of magnitude, but are really only confident that the threshold between okay and not okay is somewhere between 1 to 3 parts per million. What happens if we were to measure a phosgene concentration of 1.4 ppm? Would we feel safe to go back into the previously or still currently contaminated area? 1.4 is numerically lower than 2, but still within this uncertainty range of 1 to 3 ppm. Would we be more confident? Would we be more likely to go back if we knew that the safe limit was 2.0 ppm with a higher level of precision? Let's pretend that we're part of an emergency response team that's tasked with trying to measure the phosgene still within the air. Because it's a very highly specialized skill, we recruit a third party to do the testing for us. And we have two options. We can hire Team A, which is more expensive because they have better equipment, better techniques, are generally more precise. But we could also hire Team B, which is pretty cheap, largely because they are a lot faster, they're a lot messier, they're less precise because of their measurement techniques of the tools they use to perform these measurements and calculations. Let's take a look at the results we would get from each team. Team A, being more precise, would measure a large amount of air with a high level of precision. Let's say they measure 1,200 point liters of air. Because this number has 4 significant digits, we know that the sample of air they measured is somewhere between 1,199 and 1,201 liters. So a very, very tight range, a very precise amount of total air that they measured. They'd use a very precise machine called a gas chromatograph to detect this toxic gas molecule, and they would measure 1.41 milliliters of phosgene. Again, a high precision measurement with 3 significant digits and a very tight and small range of potential volumes that they actually measured. To do the calculation, which if you're not familiar with these types of concentration calculations, trust that I've done the measurements or calculations correctly. But we see that by calculating this concentration, the amount of phosgene per amount of air, we're left with a concentration of 1.18 ppm, 3 significant digits, because our least precise measurement, the 1.41 milliliters, has 3 significant digits as well. Let's consider a worst case scenario. Let's say we sort of got unlucky and we actually only measured on the lower end of our error window. We measured 1,199 liters of air, a smaller volume of air, and a higher concentration of phosgene, 1.42 milliliters, and again, the upper range of our error window. Recalculating this ratio, as we did before, we're still arrive at the same answer of 1.18 ppm of phosgene. We see that because we had very precise measurements to begin with, our final calculated answer was very, very precise. We know essentially that the concentration is exactly 1.18 ppm plus or minus 0 ppm as far as our calculations are concerned. Again, Team A, more precise measurements, more significant digits, a smaller range of potential phosgene concentrations. Let's take a look at Team B. Team B, being not as scrupulous, not as precise in their measurements, measures a smaller volume, only 12 liters of air, 2 significant digits. That means, of course, that the actual volume of air with error accounted for is somewhere between 11 to 13 liters. With their cheaper tool, their cheaper gas chromatograph, they measure 0.001 milliliters of phosgene, 1 significant digit. And because there's only 1 significant digit, that really means that they measured anywhere between 0 to 0.002 milliliters, twice the average value that they report. Again, fewer significant digits, larger range of error. Same calculation. Numerically, they arrive at an answer of 0.8 ppm, which is technically lower than the number that Team A got. But if we do the same worst case scenario planning, we think that they actually measured a smaller amount of air and a larger volume of phosgene. We would recalculate it as 2 ppm of phosgene, which is now at, maybe potentially above, the threshold for safety of this particularly toxic chemical. So here we see a very contemporary example and a very realistic one that has been unfolding over the last year or so, in which precision really does matter. Precision is tied into the confidence of our calculations, and by being engineers, we make many decisions based on our calculations and how confident we are in them. In this case, it is engineering, as well as some other factors, health and medicine, that determine whether or not it's safe for people to go back to their homes, to live and breathe and eat and bathe in the water that was contaminated but hopefully now is no longer contaminated, and how confident we are in our measurements and calculations. The precision and error of those measurements and calculations is something we really need to keep track of in these very, very dire situations. There are very few of us engineers who work in fields and applications that don't interact with humans, with human lives and livelihood, with the well-being of our friends and family and neighbors. And we need to make sure we keep and use these significant digits, these measurements of precision, in order to safeguard their well-being, both in this example and many in your careers to come.